conferencia. Bueno. Ah. Parece que recién se va a transmitir en vivo. Ya. Buenas tardes. Tengo el agrado de invitar al profesor postdoctorado, señor Cristian Ortiz. Ya, buenas tardes. Tengo el agrado de invitar al profesor postdoctorado, señor Cristian Ortiz, quien investiga en el área de la geometría diferencial, con enfoque en estructuras geométricas superiores. En la presentación de la investigación se ruega en lo posible que la ronda de preguntas es al final de la conferencia. Adelante, profesor.
Ok, ¿me escucha?
Sí, yo lo escucho. Voy a desactivar el audio.
¿Mejoró?
Sí, se escucha y se ve. Adelante.
Ok. Bueno, muchas gracias por la invitación. Estoy aquí con un problema de sonido. Minuto, por favor. Ok. Bueno, como decía recién, agradecer por la invitación a este congreso. Voy a hacer la charla en inglés porque me parece más fácil para poder expresar los conceptos de matemática. ¿Ok? Entonces, okay, solo para verificar que yo estaba con un problema de audio, ¿se me escucha bien?
Sí, todo ok.
Ok. Ok. So, the title of my talk is Geometric Structures on Differentiable Stacks. So I'm going to present an overview of some recent development on differential geometry on this kind of spaces, which along the way we are going to see that a differentiable stack can be thought of as a singular quotient of a differentiable manifold. And we are going to show how one can extend classical differential geometry to the setting of this singular quotients. Okay. So for that, let me start with the motivation of the problem. So we are going to, so the setup is a differentiable manifold, typically denoted by M. And this manifold comes with some notion of symmetry, which formally can be understood as an equivalence relation on this space, on the manifold, right? And as usual, we want to understand the space of equivalence classes And of course, this guy comes with a topology, the quotient topology. But the problem is that even if the manifold is smooth, even if we are in the smooth setting, we can end up with a space which is not smooth, and probably this guy is a singular space, right? So I'm going to give you some examples. So first, I'm going to talk about the good case, meaning when this quotient is actually smooth, and then we are going to move to singular situations. All right, so consider a surjective submersion. So this means that we have manifolds Mn. This map pi is surjective, but also the derivative is surjective at every point. So this allows you to construct an equivalence relation on the manifold M, and the equivalence relation is given by this. So suppose that, so this is the manifold M, and here we have N, and 2 points X and Y are related if they belong to the same fiber by pi, meaning that these two guys project to the same point in N. So that is the equivalence relation induced by pi. And in this case, one observes that the corresponding space of equivalence classes identifies with N, which by definition is smooth. So essentially, smooth quotients of manifolds are given by this kind of object, surjective submersions between manifolds. So let me move to another example in which we are going to see that the quotient has singularities. So for that, we're going to start with a manifold as usual. And now the notion of symmetry is given by the action of a Lie group, right? So then the space of equivalence classes is just the orbit space of the action. And this space is not smooth in general. So if the action is proper and free in differential geometry, we know that this guy has to be smooth. But if that is not the case, for instance, when the action is proper, but it has finite isotropy groups or finite stabilizers, there is a theorem in differential geometry called the slice theorem, which tells you that this quotient space is no longer a manifold, but an orbifold. So an orbifold means that this space is no longer locally modeled on a Euclidean space, but it locally looks like a Euclidean space modulo the action of a finite group. So here you can see a picture of an orbifold called the teardrop orbifold. And this orbifold can be constructed by gluing, by taking the sphere. You take the upper hemisphere and the lower hemisphere, and you glue them together. So here in this part you do nothing, but in the north part you make this cyclic group act by rotations. So the north pole is fixed, and then you glue these two pieces together, and you end up with something that looks like a sphere downstairs, but upstairs it has this singularity here, reflecting the fact that the north pole is a fixed point of the action. So this is the teardrop orbifold. So this is not a smooth space, and the idea is trying to do differential geometry on these guys, but also in more complicated singular quotients. Another situation in which we end up with a singular space comes from foliation theory. So suppose that we have a manifold M endowed with a foliation. So we have a decomposition of the manifold in leaves. And in foliation theory, we want to understand the leaf space, right? So again, this guy is not necessarily smooth. Actually, this guy will be smooth precisely in the situation of the first example. But for instance, if the leaves are compact and the holonomy is finite, there is a theorem in foliation theory called the Reb theorem, which tells you that the leaf space is no longer a manifold, but an orbifold. All right, so in these three different situations, we have the same pattern, a manifold equipped with some sort of symmetry. We want to understand the corresponding space, quotient space, and sometimes this quotient space is good, meaning that it's smooth again, but in general is no longer smooth and might have some singularities. So just for completeness, there is a general criterion called the Gottman criterion, which tells you precisely when the space of equivalence classes of an equivalence relation on a manifold is smooth, right? So if someone is interested in this kind of construction, you can search for the Gottman criterion, and you will see precisely conditions that ensure that this guy is smooth. But in general, it's not, okay? So, okay, we have seen 3 examples so far, and what do these examples have in common? So as I said before, all of them are given by a manifold with symmetries. We want to understand the corresponding quotient space. In geometry, we call this the transversal geometry. And the point is that this transversal geometry is encoded by a geometric structure called a Lie groupoid. So what I'm going to tell you in the remaining of the talk, I'm going to define the groupoids, I'm going to give examples, and I'm going to explain to you how you can understand the transversal geometry of this kind of problems in terms of a Lie groupoid. Okay, so more precisely, what we are going to see is that quotients associated to Lie groupoids have a very precise nature, and these objects are called differentiable stacks, which appear in the title of the talk. And our main goal consists on doing differential geometry on this kind of space. Okay. So for that, we use a variety of techniques. So let me mention some of them. So the techniques we use to understand differential geometry on stacks include higher category theory, homological algebra, simplicial homotopy methods, representation theory, strongly homotopy algebras, or also called L-infinity algebras and differential graded Lie algebras, and many other techniques whose outcome in this picture is given by, for instance, vector bundles. So using these techniques, one can understand vector bundles on these singular quotients. We can understand vector fields on those spaces. We can understand symplectic structures, Riemannian metrics. We can talk about invariants of differentiable stacks by considering cohomology theories, and many other concepts that are well known in differential geometry and topology can be promoted to the setting of differentiable stacks by using these techniques and many others. Okay, so for that we need to deal with algebraic structures and combine with geometric concepts. Okay, so let me tell you what a Lie groupoid is. So for that, I need first to recall what a groupoid is. So there is a short definition of a groupoid involving category theory. So a groupoid is a small category in which every morphism is invertible. Okay, so in a diagram, this amounts to having a space or a set of objects, a set of arrows between objects. So I'm going to draw an arrow like this. And typically arrows are denoted by G. So this point here, which is an object in M, will be denoted by SG, and it is called the source of G. And similarly, this guy is called the target of G. And because every arrow is invertible, we have an inverse arrow going into the other direction. And this arrow is denoted by G minus 1. So in terms of structural maps, one has an inversion map, which takes an arrow G and maps this arrow to its inverse. You can also compose arrows, which is denoted by this, or you can multiply arrows. And of course, you can multiply arrows if the domain and the codomain if you have another arrow here, or if you have another arrow here, you cannot compose these two guys because the codomain of this one and the domain of this one are different. But if you can concatenate these arrows, then you can make the composition, and the composition is denoted by this. And also any object can be seen as an invertible arrow by considering the identity map from the object to itself, right? So these are the structural maps defined in a groupoid. And of course, these maps have to satisfy some conditions, which tell you that actually we have a category. So in simple terms, this guy has to be an associative product, partially defined associative product with inverse I and unit 1. And we are interested in the case when the whole data is smooth. So everything here is a smooth manifold, and all the maps, the structural maps, are differentiable maps. And in that case, we are going to see that this data defines a Lie groupoid. So, and the notation that I'm going to use is precisely this one that I'm highlighting here. So we are going to say that G is a Lie groupoid over M. Okay? So let me tell you precisely how in each of the first 3 examples, one has a groupoid underlying the problem. So in example 1, if you remember, we had a surjective submersion pi between manifolds, and this submersion defines an equivalence relation on the total space of the submersion, and this equivalence relation can be seen as a subset of 2 copies of M, and this is precisely that set. So this takes pairs of points in M, having the same image by pi. So that will be our space of arrows now. So this is going to be G. And this defines a groupoid by considering the source and target given by the canonical projections. All right, so we have 2 extreme examples of this construction. So the first one is when this manifold is a point. So pi has to be a constant map. And in that case, if you take an arbitrary pair of points, these points have to be related, of course. And this defines a groupoid called the pair groupoid. In the case when this manifold coincides with M and pi is the identity, then this graph is precisely the diagonal inside 2 copies of M. So I'm going to identify the diagonal with M itself, and this defines a groupoid with source and target given by the identity, right? So essentially this tells you that any manifold can be seen as a groupoid. Okay. There is another example which appears quite often in this theory, and it is associated to open covers of manifolds. So associated to any open cover of a manifold, you have a canonical surjective submersion. And if you construct the submersion groupoid associated to this guy, you end up with an important groupoid called the check groupoid. So this groupoid allows you to glue information to pass from local information to a global information by glue them together. The second example of a Lie group action. So if you have an action on a manifold, then you can construct a groupoid whose space of arrows is given by this Cartesian product, and the space of objects is M. So here the source map takes an element in G and an element in X and projects to X, and the target is given by the action. So this is also a groupoid called the transformation groupoid. And there is a particular case here, which is the case when M is just a point. So then, of course, you have a trivial action. And in that case, this thing can be seen as a groupoid by considering G over a point, and source and target are constant maps. So in particular, any Lie group can be seen as a groupoid. Because of the previous example, any manifold can be seen as a groupoid, and because of example 2, a Lie group acting on a manifold can also be seen as a groupoid. Okay, so spaces, symmetries, and spaces with symmetries can be encoded in terms of Lie groupoids. So for the third example, so any foliation defines two groupoids called the holonomy groupoid and the monodromy groupoid. So I don't have time to define these guys, but essentially what you take here, so you take points living in the same leaf, and an arrow will be a holonomy class of a path between these 2 points. And this guy, instead of considering holonomy classes of paths, you consider homotopy classes of paths. Okay. So let me tell you how one can attach to a groupoid transversal information. All right. So let us start with a groupoid, Lie groupoid G over M, and fix a point in M. So one can talk about the orbit through the point X, denoted typically by OX. And these are all the points in M which can be reached by an arrow whose source is precisely the point X. Okay? So that is the orbit of the point X. It is a subset of M. Actually, it is a submanifold of M. These orbits are disjoint, and actually orbits are the equivalence classes of an equivalence relation on M, defined by this. And one can talk about the corresponding quotient space, denoted by this. So this is referred to as the orbit space of the groupoid. And of course, this guy is a topological space with the quotient topology, but it is not necessarily a manifold. Okay. So what we want to understand is the singular nature of this quotient. All right. So also associated to an object in M, its isotropy group, which consists of loops with base point X. So it is an arrow with source X and target X. And also another ingredient in this transversal information is given by the normal representation. So the isotropy group acts on the normal directions to the orbit. So suppose that we have here an orbit and point X in here. Now you take a normal direction, which is this quotient space here. So it is the tangent space to the manifold mod out by the tangent space to the orbit. So I draw this like this. And it turns out that the isotropy group G acts on this vector space by linear isomorphisms. So in other words, what we have is a representation of this Lie group, and this representation is called the normal representation. So if you're familiar with the slice theorem in group in the theory of Lie group actions, so this is precisely the stabilizer of a point, and this is precisely the isotropy action of the isotropy group. Or if you're more familiar with foliation theory, then this representation here is given by the holonomy representation of a leaf. Okay, so this bunch of information is what we want to understand, and we call this the transversal data associated to a groupoid. And our main goal is to study Lie groupoids having the same transversal data. So what do I mean by the same transversal data? So by the same transversal data, I mean that homomorphic orbit spaces, isomorphic isotropy groups, and isomorphic normal representations. Okay, so that will mean having the same transversal data. Okay, so one can do a remark regarding this goal, and the remark is that if you pick up a groupoid morphism, then this groupoid morphism induces a morphism between transversal data. So I didn't say what is a groupoid morphism, but it is just a differentiable map between manifolds. And since these two guys are categories, we require this guy to be a functor. So it is a smooth functor between categories. That is a Lie groupoid morphism. And an easy exercise is checking that actually such a guy induces a map between the transversal data. So you will have a map between orbit spaces. You will have a group map between isotropy groups, and also you will have a map between the normal representations. So an intertwining map. So now that we know that the transversal data is functorial, we want to characterize those Lie groupoid morphisms which induce isomorphic transversal data. And that is a theorem by a collaborator of mine, Matias Del Hoyo from Rio de Janeiro. And the theorem says that a groupoid morphism induces an isomorphism between transversal data if and only if this groupoid morphism is a Morita map. So a Morita map is a smooth version of a fully faithful functor and an essentially surjective functor. So, and we know from category theory that fully faithful and essentially surjective is equivalent to being a categorical equivalence, but in the smooth case, that is not necessarily true, but we look at maps which are smooths, which satisfy a smooth version of being fully faithful and a smooth version of being essentially surjective. And these guys are called Morita maps. But for the purposes of this talk, you can think of that a Morita map is just a smooth equivalence of categories. All right, so now we will look at an equivalence class of transversal data. So it is the isomorphism class of transversal data. And we want to understand this guy, okay? So we want to understand in which sense this guy can be seen as a space or as a manifold or something. And there is a categorical approach to this objects, which comes from with roots in algebraic geometry. So and what happens here is that this guy is actually a differentiable stack. So stacks were introduced in algebraic geometry, and we need some categorical machinery to give a precise definition. But I will just mention here some of the ingredients of the definition. So a stack is given by a fibers category. So this is a fibration in categories. So this guy is a category. This is the category of manifolds, and this fibration satisfy a gluing condition. And to make sense of this gluing data, we need to endow these categories with something that is called a Grothendieck topology. So we have here categories with Grothendieck topologies and satisfying some conditions. This kind of spaces are fiber categories with an additional structure called an atlas, which is given by a representable epimorphism from a manifold to this guy. And being representable means that when you take fiber product of stack of categories, this guy here is actually a Lie groupoid. So essentially, if you ignore this complicated information, the geometric concept behind this notion is precisely a groupoid. Okay. And if you choose a different atlas, of course you will have a different groupoid, but these two groupoids are related in the sense that they have the same transversal data. So one can think of now the isomorphism class of a transversal data, like as I explained before, or in terms of stacks. Oops, sorry. So let me put that more precisely. So there is a one-to-one correspondence between differentiable stacks up to isomorphisms and Lie groupoids up to Morita equivalence. Being Morita, two groupoids are Morita equivalent if they have the same transversal data. Okay, so under this dictionary, when we look at étale and proper groupoids, on the left-hand side, one has orbifolds, which are the differential geometric counterpart of the so-called Deligne-Mumford stacks in algebraic geometry. All right, so for the purposes of this talk, we want to do differential geometry on this side of the picture, okay? So for instance, if we want to define a geometric structure on the left-hand side of the dictionary, we are going to do that by considering the same type of geometric structure on a groupoid, but this geometric structure has to be compatible with Morita equivalence. Or if you are interested in defining invariants of a differentiable stack, simply you have to find Morita invariant of a groupoid. Morita invariance of a groupoid. Okay, so we're going to take this side of the dictionary and we are going to define geometric structures on groupoids up to Morita equivalence, and we want to see some Morita invariants. Okay. All right, so let me move to differential geometry on stacks. So the first thing when we deal with geometric structures on manifolds, it is very important to understand another manifold associated to a manifold, and that another manifold is called the tangent bundle. Right? So using the tangent bundle, you can make sense of Riemannian metrics, tensors, differential forms, polyvector fields, foliations, and many other things, right? So Well, for stacks, there exists such a construction, and it's called the tangent stack, which is defined using this kind of terminology. So it's not that easy to understand, but the tangent stack is well defined. And one question that I was wondering some years ago is if there exists a notion of a vector bundle over a stack. Then I learned about this work by Darren, Gino, Nouhi, and Xu. And actually, they have a notion of a vector bundle over a stack, but this definition has a gap. So this is well defined, but the tangent stack, which is probably the example that you want to include in this setting, is not necessarily an example of a vector bundle, unless in the case of orbifolds. So then I started to discuss with my colleague Matias Del Hoyo from Rio, and we wanted to understand a good notion of a vector bundle over a stack, including the tangent stacks as an example. So, and we did it, and this is part of a publication of last year and the International Mathematics Research Notices. And what I want to tell you now is some of the ideas of our work with Matias. Okay. So in general, when you have a manifold or a set, let's say a set with an equivalence class, and you want to define an object on the corresponding orbit space, you look at the same type of object before modding out by symmetries, but you require that this object is invariant by the equivalence relation, right? So, and then you show that if this object is invariant by the corresponding equivalence relation, then it descends to a similar object at the level of orbits. Okay. So for that, we said, okay, we can look at vector bundles equipped with an action of a groupoid. So these are called groupoid representations. So a groupoid representation is a vector bundle on the manifold M. Remember that having a groupoid immediately gives you an equivalence relation on M. And 2 points are equivalent if they are related by an arrow. So that's the equivalence relation. All right, so now we look at a vector bundle on this space in which the equivalence relation is defined, and this vector bundle has to be compatible with the equivalence relation, right? So that is precisely the notion of a representation. So here, a representation will be the following association. So the following assignment. So you take an arrow of the groupoid going from X to Y, and you will make this guy act as a linear isomorphism from the fiber of E over X to the fiber of E over Y. So that is a linear isomorphism between fibers, and you require that it satisfies the action axiom. So meaning that if you call this guy, let's say, phi G, then the product phi G H acts by the composition. Okay, that is the action axiom. All right. So out of this data, you can construct a groupoid, which is just the transformation groupoid that I explained before. And it turns out that the space of arrows of this groupoid is actually a vector bundle over G. We already knew that this guy is a vector bundle over M, And actually, this diagram here defines a vector bundle in the category of groupoids. So that is called a VB groupoid. So representations, which are the objects that we just defined, gives you naturally a vector bundle over this groupoid, which is something that we wanted to understand before. So let me give you an example of a VB groupoid. So if you start with a groupoid G with source S and target T, then you can apply the tangent functor and you end up with another groupoid called the tangent groupoid. And it turns out that this diagram is also a VB groupoid, a vector bundle in the category of groupoids. But this guy does not necessarily come from a representation. Okay? So our original idea of looking at representations in order to define vector bundles does not suffice because we want to include the tangent stack. And we want to include in order to include the tangent stack, we want that the tangent groupoid be the groupoid inducing the tangent stack. Okay, so, but this guy does not necessarily come from representation, so usual representations do not suffice. So a remark is that this VB groupoids over G form a category, as usual, in morphism of vector bundles, and which are groupoid maps as well. And because of that example, we need a more flexible notion of symmetry in this setting. So the idea is this: we are going to use a notion of representation up to homotopy defined by Arias and Kreinig, and independently by Gracia-Sass and Mehta. And the idea here is that arrows of a groupoid do not act on the fibers of a vector bundle, but now they act on the fibers of a complex of vector bundles. So we will think of this as a homological complex concentrated in degree 0 and degree -1. So the other parts of the complex are 0. And now arrows act on fibers of this complex, right? And they do not act by linear isomorphisms between complexes, but they act by quasi-isomorphisms of complexes, meaning that in homology, we have an isomorphism. The notion of representation up to homotopy is basically this, and the action axiom is no longer true in this case, but the product act by the composition up to a homotopy of complexes. So there is a homotopy of complexes relating these two chain maps. And this homotopy satisfies some higher coherencies, and well, I do not have time to define this precisely, but the idea is that now you replace vector bundles by complexes of vector bundles, and arrows do not act by linear isomorphisms, but they act by linear quasi-isomorphisms, and the action axiom holds up to homotopy. And because we have this complex has length 2, we call this representations of length 2, and they form a category. And the point is that now this example that does not come from a representation, actually this guy can be recovered in terms of a representation up to homotopy. So how do you recover that? By using something called the Grothendieck construction. So whenever you have a representation up to homotopy, you can construct a vector bundle in the category of groupoids, right? And what we managed to show with Matthias is that Grothendieck construction actually gives you an equivalence of categories between representations up to homotopy of length 2 and vector bundles over groupoids. Part of this equivalence actually was shown by Gracias and meta at the level of objects. But then we recognize this correspondence between objects, isomorphism classes of objects, as actually an equivalence of categories. Okay, so our insight was correct. So if you want to work now with vector bundles over groupoids, you can either work with these objects or with representations up to homotopy. Well, the point is that if you want to work with stacks, you need to make sure that your objects are Morita invariants. And this category is not Morita invariant because actually the category of vector bundles is not Morita invariant. And when we observe that, then we believe that probably the derived category of representations is actually a Morita invariant. And that is the content of the second theorem. So whenever you have, it's a technical theorem, but if you promote the notion of Morita maps to vector bundles, then having a linear Morita map between vector bundles over groupoids is precisely the same as having a quasi-isomorphism of representations up to homotopy. So it is something that is Morita map in the basic part of the bundles, and in the fibers, this guy is a quasi-isomorphism. Okay, so this theorem has some consequences. So we use this result to show that Morita equivalent groupoids have the same deformation theory. We use this result to understand cotangent symplectic reduction as an instance of Morita equivalence. We also use this result to give an alternative simple proof of the integration of Dirac structures. And also with this result, one can make sense of symplectic structures on stacks. And these symplectic structures are called one-shifted symplectic structures. So this result allowed us to get applications in deformation theory and symplectic geometry and Dirac geometry. But the main consequence is that the derived category of representations now can be geometrically understood as the category of vector bundles over groupoids localized along linear Morita maps. This is precisely the content of this theorem. Okay, so in categorical terms, it's the theorem can be rephrased by saying this. Okay, so now when you have, I want to explain in which sense these derived categories are Morita invariant. So if you take a Morita map between groupoids, then the pullback of vector bundles induces a map between VB groupoids, and you can show that this map descends to the localization along Morita maps. So this is a category, this is a category, and if phi is a Morita map, then this functor is actually an equivalence of categories. So that means that although the category of vector bundles over a groupoid is not a Morita invariant, what is actually true is that the derived category of vector bundles is a Morita invariant. And because of the previous theorem, one concludes that the derived category of representations is a Morita invariant. And actually, this was an open problem in the representation theory of the groupoids, and we managed to show to solve this problem by considering geometric structures on the groupoids. All right. So now, to finish, if we have a stack given by a Lie groupoid, then we are going to define the category of vector bundles over that stack as the derived category of vector bundles over the groupoid G. And because this guy is a Morita invariant, this category is well defined. And now we have good properties of this category, and now the tangent stack is actually an example. It can be understood by using the tangent groupoid, but also now we can understand the cotangent stack in terms of the cotangent groupoid. Let me tell you some other results that came after this work with Matthias. So in a joint work with James Waldron from UK, we managed to prove a conjecture on the structure of vector fields on differentiable stacks. And actually we proved something more general, but we used these ideas to understand this kind of objects. In a joint work with Matthias and a former student of mine, Fernando Studzinski from São Paulo, we extended our results to the case of simplicial vector bundles. This is necessary because if you take two vector bundles over a groupoid and you look at the tensor product of vector bundles, this tensor product is no longer a VB groupoid, but a simplicial vector bundle over the nerve of the groupoid. Right, so we managed to extend these results to this setting. Matthias also has some work with Fernandez from Illinois on doing Riemannian geometry on groupoids. More recently, a postdoc, Alejandro Barbosa from the University of São Paulo, together with Frank Neumann from Leicester, they introduced equivariant cohomology in the setting of stacks. And finally, let me mention a work with my student Sebastián Herrera from University of São Paulo, and in this work we use these ideas of using groupoids to understand stacks in order to introduce characteristic classes of differentiable stacks by extending the classical Chern-Weil map in differential geometry. So this is what I wanted to say. So thank you very much for your attention. I don't know if there are questions. ¿Se fue el moderador?
No, estoy aquí. No hay preguntas, parece, don Cristian.
Nadie tiene preguntas.
Bueno,
bueno.
Gracias por su participación, Cristian. Por el CONCA 2021. Bueno, no hay preguntas, parece.
Bueno.
Ya, gracias.
Gracias por la invitación.
Ya, gracias por cooperar. Gracias, hasta luego.
Hasta luego.
Ya.